Hello everyone, thanks for coming to our talk. My name is Jang, and I'm a PhD student at University of Michigan. I'm working with Professor Necmiye Ozay and Johanna Mathieu, and the title of my work I'm going to present today is Large-Scale Invariant Sets for Safe Coordination of Thermostatic Loads. One important issue in power system right now is the rapid increase of renewable energy generation. As the number of distributed energy resources, such as solar panels, is increasing, it is becoming more difficult to balance between the demand and supply. To relieve this issue, electric loads over the distribution network can help the grid by providing services. For example, thermostatic loads such as air conditioners and heaters can help the grid by adjusting their power consumption in response to the system operator's request. However, when they are doing that, they should not violate some constraint and threaten the safety of the network. For example, as a local constraint, the temperature of thermostatic loads should not deviate from their target temperature a lot. And as a global constraint, the voltage of every node at the distribution network should be in a safe range of voltage. And therefore, we need to develop a controller of these loads, which keeps the safety of the system to let them provide service to the grid. One way to synthesize a safe controller for a system is to use a controlled invariant set. A set Xi is a controlled invariant set if it is a subset of the safe set, and every element of it has at least one input u, keeping it inside Xi at next time step. And it is shown that if the initial state is in a controlled invariant set Xi, there should be at least one sequence of input keeping the state inside the safe set. Using this property of controlled invariant set, our work develops a safe controller as following procedure. First, we develop a method which computes a control invariant set of the system with a group of multiple homogeneous systems. Second, we develop a safety guaranteed control algorithm for these loads, which keeps the state of it inside a control invariant set. Before we get into the details, we introduce a list of related work. There are some good work which developed a controller for thermostatically controlled loads to provide service to the grid. However, they either didn't consider the safety constraints on distribution network or didn't have formal safety guarantee in their algorithms. And there are also some work which propose ways to compute an invariant set for a linear system. However, these approaches cannot be used for high-dimensional system because of their computational complexity. In contrast, our work proposes a scalable invariant set construction method applicable to a large-scale system and a safety guaranteed control algorithm. Now let's see the system setting of our work. We consider a system with a group of multiple homogeneous thermostatically controlled loads, which we will call as TCL. The state of each TCL is the temperature, and the mode of each TCL is either turned on or turned off. And the temperature evolution dynamics changes as the mode changes. Also, we assume that this group of TCLs has two constraints. First, a local constraint on every TCL exists, that the temperature of every TCL should be in a certain range of temperature, which is represented as this blue area in this figure. Also, there is a bound on the amount of total power consumption of these TCLs for the safety of the distribution network, which is represented as this inequality, where P is the power consumption of one TCL and N1 is the number of turned on TCLs. By dividing this inequality by small p, this inequality can be transformed to this inequality, which means that the number of turned on TCLs should be between both lower bound and upper bound, where they are defined as follows. Then our objective under this setting is to develop a controller for the TCLs, which never let them violate the constraints while providing balancing service to the grid. So the controller here should receive a reference signal from the system operator and control the mode of each TCL in a way that they can provide the balancing service as this graph on the right side. Suppose that this blue signal in this graph is the reference signal from the system operator, which is generated between the forecasted power bounds represented as this horizontal dotted lines. However, if an unexpected event happens in real time, the safety bounds on power can shrink to these solid black lines. In this case, the controller should control these TCLs in a way that their total power consumption becomes like this orange dotted line here, which closely tracks the reference signal while it never violates the safety bounds on the power consumption. But instead of developing a safe controller only for this demand response problem in power system, we work on a broader and more general class of problem. We first assume that we have a product transition system which is defined as a group of multiple homogeneous transition subsystems with multiple modes, like this figure with two-dimensional state subsystems. We also assume that this product transition system has two constraints. The first one is that the states of all subsystems should be included in a safe set of states, which is represented as these blue circles in this figure. Also, the number of subsystems in each mode is bounded by both upper bound and the lower bound. Under these constraints, we also have a cost function C we want to minimize. So our objective in this generalized setup would be to develop a safe controller for this product transition system, which minimizes the cost while satisfying all the constraints here. As the first step, we construct a state abstract version of this subsystem. We first divide the state space of it into multiple same-size squares, and then we only keep the center of these squares as the abstracted states. And the size of these squares and the transition relationship between these abstracted states should be determined in a way that these two subsystems here have some level of bisimilarity. In addition, the safe states of this abstracted system are determined in a way that this abstract system has a more conservative safety condition than the original subsystem here. Now we construct an abstraction of the original product transition system by changing each subsystem to the abstract subsystem like figure below. Then from the bisimilarity of these two product transition systems and more conservative safety condition of this abstracted version, what we can show is that if a controller of this abstract product system satisfies all the constraints, then that controller is also safe for the original product system. This motivates us to develop a safe controller for the abstract product system first, because it would be also safe for the original product system. So from the next slides, we are going to develop a safe optimal controller for the abstracted product system first. To do that, we use an alternative representation of the abstracted production system, which is named as aggregate system. Let the state X be the vector whose elements are the number of subsystems in each mode at each discretized state, and U be the input whose elements correspond to the number of subsystems changing mode at the time step. Then the dynamics of this state X can be represented as the following, where the matrices A and B are determined by the transition relationship between the states. We also can define a safe set of this system X safe, which includes every X corresponding to when the system satisfies all the constraints. Now, what we want to do is to synthesize a controller which keeps the state X inside this safe set X safe forever. To do this, we first have to construct a control invariant set of this aggregate system. Now, I'll explain a high-level idea of our invariant set construction method. Our method uses cycles of the abstracted subsystems to generate a set of state whose every element has a periodic input sequence keeping the state inside the safe step. Then what it can show is that this generated set Ximp becomes a controlled invariant set of this aggregate system. This is a really brief explanation of our method, and if you're interested in the details, please read our paper. And finally, we can synthesize the following control algorithm, which is named as invariant set-driven MPC. So this problem is similar to the basic MPC, but the difference is this additional blue constraint. If you see here, h is the length of the horizon of MPC, and xt plus h bar t corresponds to the last state in the horizon. Therefore, this constraint requires the last state in the horizon to be included in the controlled invariant set Ximp. By adding this constraint, we can prove that the state trajectory from this algorithm never leaves the safe set, and this optimization problem is always feasible at every time step. One more important thing about it is that the number of subsystems does not affect the amount of computation for solving this optimization problem, and therefore our algorithm is applicable to large-scale systems composed with a lot of subsystems. Now, I want to introduce a result of our one numerical experiment where invariant set-driven MPC and two benchmark control algorithms are compared in terms of the safety of the system and the tracking performance in demand response problem. In this simulation, we consider the case that this blue reference signal in this graph is generated in advance between the forecast bound, but an unexpected issue has happened at the distribution network so that the safe bound on power consumption becomes this horizontal solid black lines, so that the reference signal becomes untrackable at some point. For the benchmarks, the first one uses basic MPC but truncates the reference signal so that it can always be inside the safety bounds. And the second one is similar to invariant-driven MPC, but it requires the state at every time step to be included in ximp, which is more conservative than our algorithm. If you see the power consumption of TCLs from benchmark 1, which is represented as these red dotted lines here, you can see that it violates the safety bounds at some point. But if you see the result of benchmark 2 and invariant-driven MPC, they didn't violate the safety constraint. On the other hand, we observed that the invariant-driven MPC has better tracking performance than benchmark 2 by comparing tracking error of benchmark 2 and invariant MPC. Therefore, we can conclude that our algorithm has better performance than the benchmarks in that it never violates the constraint while having better performance. In conclusion, we have developed an invariant construction method for an aggregation of multiple homogeneous systems, which is applicable to a large-scale system, and a safety guarantee control algorithm. As the future work, we want our problem setting to be more realistic, such as time-varying constraint and the heterogeneous subsystems. And here's the list of the reference. Thanks for listening.